And our first presentation is from Sabine Gebersdorf from Stuttgart, who did her work, and her team did their work at the University of Hull, and her paper is entitled Exploring the Reciprocal Role of Hydrodynamic Forcing and Microbial Colonization to Induce Bed Sediment Patchiness in Biostabilization. Thank you.
Yeah. Thank you very much, especially for reading this long title. Yeah, ladies and gentlemen, good afternoon. Today I would like to introduce you a bit more into the microbial world, as you can see already from the title. And as we all know, there is not just one way to look at things. Nature is complex, and if you would have just one perspective from one discipline, you would never understand how things go. And this is the reason why we are here. This is HydroLab about. So you all know that flow, for instance, and sediment greatly impacts whether organism can successfully settle and adhere to surfaces. And on the other hand, while these organisms grow, they shape their environment and they change flow conditions and possibly substrate. And while we recognize more and more that biology is indeed of huge consequences, we focus mostly, as humans do, on the stuff we see. So for instance, as we have seen this morning, on this afternoon, on macrophytes, the big stuff you can grab. And for sure they have influence, they are lovely sediment traps. And for sure macrosorbentos, which you can also easily see and grab, has a huge impact. But last but not least, the small stuff, the microbes, have some consequences too, although you don't see them very well. They lack generally the individual biomass, but they make up for that in numbers. Now, if you want to look at one of the human megacities, for instance Shanghai, you see there are lots and lots of inhabitants. And if you compare that to a biofilm, then you would see all those inhabitants and much more would fit in one skyscraper of a biofilm city. So you can see this huge biomass must have some impact. Moreover, these biofilms are not just distinctly distributed, but ubiquitously distributed. And they are the first colonizer. They prepare the ground for other colonizers, for the bigger guys. But last but not least, they have a huge impact on sediment because, as we heard already today, they secrete what we call polymeric substances. Some call it mucus or slime. And these polymeric substances, they basically glue the sediment particles together. This is what you can see here. These were actually glass beads, sparkling clean glass beads, which are covered by EPS from a biofilm just within days. And here you can see on these two slides diatoms. I'm glad the word was already mentioned by the lady before me. And the diatoms also secrete some EPS. They do so to move on that, while bacteria, for instance, secrete that to stay for good. So now that I convinced you that they do secrete something and they do something with the sediment, I would like to show you our experiment. Now you have seen already the total environmental simulator. I can spare some time on that. What you haven't seen is now our experiment. So that means on the right side, before the experiment could actually start, we had to do some building work. There were some concrete building to be done to put in groyne fields. And now because of the lack of time, I don't want to go into details, but I just want to use this overview to show you that we had not just one groyne field set up, but several ones. This is so you could have undisturbed groyne fields where you could do some non-destructive measurements and others which you could basically sacrifice for sampling. Now, why groyne fields? Groyne fields, as you probably better know, I'm the biologist here, they have a distinct flow pattern a very characteristic flow pattern, and this very likely induces sediment segregation, different sediment patchiness, which also likely induces different biofilm growth. And therefore, we have chosen this groyne field setup. Now, what happened in the experiment in the first phase? First of all, there was sediment put into the flume, and it was a bimodule sediment consisting of sand and gravel. And now this was well mixed, so it had to segregate, and that was done by increasing the flow. And there were basically three main flow steps, if you want, up to 250 liters per second. And the flow was then measured at each of the flow steps with ADV probes. And what you see here is just one example done or determined under the highest flow condition. On the left side, you can see, hopefully here, the main channel. And here is one of the groyne fields. And the vectors, the velocity vectors, indicate already the direction. Maybe that's not so good to see from behind, but the direction is unidirectional in the flow channel. And then you have this induced circulation pattern in the groyne field. And easily to be seen by the colors, the velocity magnitude decreases very much in the groyne field as well. The turbulence, so I was told by my colleagues, has been measured longitudinal, lateral, and vertical. The right image is a vertical turbulence measurement and basically shows as well a reduced turbulence in the bay. After the sediment segregation phase, the bed elevation was measured by URS probes. And what you see here in these images is the change in bed elevation over time and over the different flow conditions. And you can see that under 180 liters and even more, you see already the erosion, the main erosion in the main channel, sorry, and at the same time the deposition of sediment in the base. And if you have a look at the rear image on how it looked like, you can also see that not only the bed height changed, but also that the substrate distributed differently. We had spots of just gravel mixed with sand and sand. And also, this is maybe important to point out, this was symmetrical between both sides, so that we could really make use of all the bays we had right and left of the channel. This is just briefly to show you where we had or where we indicated certain spots where we do some sampling. I would refer in the next slide to 1, 2, and 4, and this was basically 1 a sand dune, and 2 was more a valley of sand, and 4 mixed sand and gravel. Yes, and then finally, for me, the biofilm was allowed to grow. So there was different water used from the aquarium, which brought in lots of nutrients, and the biofilm developed over time. And as you can see, this is the time series from week 2, basically week 2 after we had the aquarium water down to the end of the experiment, week 4. It looks a bit uniform, and indeed, this does not really betray you. But let's have a closer look how the biofilm growth looked really. And therefore, I brought you here two parameters. On the left side, you have this complicated term, extracellular polymeric substances, the EPS. They consist not only of sugars. Most of people do determine only sugars. We determine more, but I brought you sugars here. And on the right side, you see chlorophyll A. With all problems, chlorophyll is a good proxy for microbial biomass. So this is an indicator of biomass. You see both EPS and chlorophyll over time. The x-axis refers to the time. Now, and what you can easily see, even as a non-biologist, the biofilm grows. There is an increase in biomass and there's an increase in EPS. This is one thing. The second thing you might recognize, oh God, there are very little differences between the fields. And this is statistically true. There were no significant differences. However, when we looked closer to the data, we saw at least some tendency that with a decreasing flow within the bay, the biomass got a bit higher, was increasing slightly, and the EPS was increasing slightly as well. But you can prove that statistically. And this all becomes clear if you look at the numbers, maybe not for all of us in this room, but the biologists will immediately recognize that the numbers are quite high. That means these are chlorophyll values and EPS which you find from eutrophic rivers or intertidal areas with very pronounced microbial mats. And this is because we had the water from the aquarium which was really full of nutrients, and therefore you have to imagine that these guys can flourish, they have plenty of nutrients. What they are really limited on is substrate. So they were looking for the last space to settle on. And basically space was here the limiting factor because of the high nutrient load. Therefore, unfortunately, they mask what we was hoping to find, a preference for substrates. And again, we only see a small preference in terms of flow. What we also measured, and this is of course hopefully the interesting stuff for the engineers, is how well they glued the sediment particles together. Now we could not erode the flume, then the experiment would be damaged forever. We used a different device, and very briefly, this is what we call a MagPI, developed in Scotland, so the name fits. It's a magnetic device, an electromagnet, which is positioned above the biofilm. Then ferromagnetic particles are spread on the biofilm surface, and then these particles are retrieved by the electromagnetic force. It's very simple. The more force you need, the more sticky the biofilm is, the more adhesion you have. Now, with this in mind, I show you the data on the adhesion which we got by this MagPI. On the right axis, you see again the x, the time. On the left, the ampere. It's calibrated against the Gauss meter and for Tesla. But here we just show you the ampere. And what you can see is a steep increase in the adhesion in the very beginning of the biofilm growth. This is very clear. The organism attached, they want to grab, they want to get a hold, so they stabilize like hell. And then they smooth down a bit, and then there is a steep increase again towards the end of the experiment. Now, there is a lovely correlation between the adhesive capacity of the biofilm and the biofilm biomass and EPS, but this relation is not one-to-one. So all I'm saying here is that quality matters more than quantity in terms of adhesion. But we saw here a good adhesion up to a factor, partly up to a factor of 10 or 12 in some measurements. In the mean, yeah, maybe only 8 or something like that. Although we were a bit disappointed that we couldn't show the preference for the biofilm for certain substrates, what we could show is that when the biofilm grew, it affected the hydrodynamics. So the second part of the reciprocal mutual influence could be shown. And here you can see what you know probably better than me, images of the turbulent kinetic energy. The left side, on the upper part, the left side is the beginning of biofilm growth. The right side is the end of biofilm growth. And on top there is the velocity image. So from the change in colors, you can already see that there is a decrease in the turbulent kinetic energy due to biofilm growth. Then I would like to sum up, and astonished, I'm quite hopefully in time. So what really has worked very well, we had a special flow pattern for the groyne fields, as we expected that. We had a pronounced sediment segregation, so also very good. We had a lovely biofilm, a bit too much for my personal taste, but here you go. Biofilm settlement and development could be shown. And because the biofilm developed so very, very, very lovely, we could not see any significant interaction between the substrate and the flow. However, again, we saw a tendency that the biofilm does increase with decreasing flow. And what I totally forgot to say, what I totally forgot to mention, that's being nervous, the adhesion capacity was negatively correlated to the flow intensity. Yeah, so that no, to the flow intensity was positively correlated, sorry. That means in the spots where we had the highest flow, there was the highest adhesion, although we had there tendency the lowest biofilm mass and the lowest EPS. And that basically underpins that it's not about quantity, it's about quality. And we need to follow these results, of course, everybody says that, but I think there's music in the research looking at the microscale, at the interaction of hydrodynamic and sediment morphology and biofilm. Nobody has done that really so far because we lack the methods, especially on the biological side. Now we have molecular tools to give bacteria even names. We have to do that. I think this is a great field of future research. And what I also meant to say, the biofilm significantly increased the adhesive capacity, and we know from own experiment that this also correlates to stability, and this shows for me once more that microbial colonization is very important in sediment dynamics. Thank you very much. Thank you also, or thanks also to some people from HAL, which were not associated with the program, but helped us a great deal, very friendly people in HAL, I have to say, and thanks to HydroLab and to you for your attention.
Right, thank you, Sabine. We have time for a few questions. Yes.
Well, indirectly, at least a hydrodynamics question, because I can't ask any biology questions really with me. But although Rob whispered into my ear, but where did you measure the hydrodynamics?
I think the plots that you saw there are all from a fixed height measured throughout the embayment. But there were also a set of profiles, which they haven't shown yet. But there are a set of profiles on different parts of the embayment. Off the top of my head, I think it's 40 millimeters off the bed, I think. So not right next to the bed, no. I think. I'd have to check that.
Okay. Other questions? We'll take the biological question first, if that's all right.
Thank you. What is the composition of your biomass? Is diatoms? Only diatoms? Yes.
Sorry, I'm just losing things as well.
Yeah, thank you. That's a very sportive job here. No? Yes, normally you have a bunch of organisms, but you're right. The dominant group always is diatoms, also in rivers. Here it was more saline water, but never mind. But due to the nutrient-rich water, it was actually a one species show, I have to say. It was Nitzschia palea, which dominated and which is very well known to flourish in eutrophic waters, and all the others, they basically didn't stand a big chance. There were some others like amphora and coconis, but really very, very low abundances. We haven't done the bacterial profiling yet, but we want to do some DGGE and fish to give the bacteria also names, but this hasn't been done yet. Not all done.
One more. Can I? Is that to follow this? Because there is a question behind you.
It will be also a biology question, although simple, I think. No, I don't understand. You say you have the eutrophic condition, so why it's not possible to reduce the nutriment or to improve the oxygenation of water in the experiments?
I should give this question to Dan, but I'm not that unfair. Yeah, this is a typical thing. Well, I think it was mentioned this morning that different disciplines have different languages. So we had a lot of discussion in pre-rounds before the experiment started, and I did point out that from the biological point of view, it would be very good to have cleaner water. While the engineers thought, oh, that's stupid, why should we should we not use the water from the aquarium? So we thought we ended up on a compromise, and then there was some misunderstanding, and sometimes things go wrong. So yeah, sorry for that, but in the end, this is something I learned I need to be more firm. I think I was too weak, saying, oh, it would be lovely to have no nutrients. Next time I should say, you make your damn stuff your own if I don't get clean water.
Yes, very. It never rains in Hull. I think we have to stop the discussion there. Thank you very much, Sabine. That was brilliant. Thank you. Our next talk comes